Welcome to April. Today I'm going to talk about, that was a weird way to say that. I was going to say talk a little about Newton's law of universal gravitation. But before I do that, I've got to give you a little bit of background. Sir Isaac Newton was probably the most brilliant physicist in all of history, with the possible exception of Albert Einstein. There are many other brilliant physicists, of course, but his knowledge and understanding of the universe really expanded what we as a species know greatly, not just in terms of his laws of motion, but many other things in physics. And he co-invented calculus independently with someone named Alfred Leibniz. So it's amazing. He did that just to explain the physics. At any rate, his law of universal gravitation is something that's really traditionally taught in high school physics classes and first-year college physics classes. It's important because there really are only four fundamental forces of nature, and gravitation is one of them. We haven't talked about any of the fundamental forces of nature yet this year. We've talked about different types of forces, contact and non-contact forces and things like that. But it truly is a universal force. The other three forces are electromagnetism, the strong nuclear force, and the weak nuclear force. And you might say, well, I've not even heard of many of those types of things. How is that possible? When I put my hand down on the table, something like that, I feel a force. Isn't that a fundamental force? It is if you look very closely at it. In fact, most of our contact forces are due to electromagnetism. The electrons and the atoms on the outside of your hand and the propelling, which are negatively charged, by the way, for electrons, end up being repelled by the negatively charged electrons on the outside of the atoms of the surface of the table. And they get very, very close. So in a way, you never really touch the table. You get very close to it, and there can be energy transferred, why it feels warm or cold. But that's an electrostatic repulsion, which is really pretty interesting. Gravitation is something, though, that was one of the first rules described in the 1600s. It was described mathematically by Newton, and experiments were done. Well, it wasn't described mathematically by Newton. It was described mathematically by Lord Cavendish from England, who did some amazing experiments a number of years after Newton was already passed away. At any rate, when we think of this, we want to think about the gravitational force between any two objects. It could be two rolls of tape. It could be a tape and a calculator, things like that. So the first thing to understand about gravitation is it is only an attractive force as far as we know. So the other three fundamental forces, which are strong nuclear force, weak nuclear force, and electromagnetism, can be attractive and repulsive under different conditions. Gravitation is only attractive. The other thing that's weird about gravity compared to the other three fundamental forces of nature is it's much, much weaker than the other forces. We don't understand that very well, meaning nobody understands that really well. So for example, if you think about it, this calculator and the Earth are attracted to each other. If I drop the calculator, it accelerates to the Earth at around 9.8 meters per second squared. But if I hold it up, I can lift this up easily. So the whole Earth is pulling down on this calculator, and the muscles in my pretty small arms are able to overcome that force of gravitational attraction from the entire Earth. That's one way to tell you that gravity is a very weak force in terms of the universe. What factors affect the gravitational attraction between two objects? So we'll pick this disinfectant and this different type of disinfectant. So as you might think, the amount of stuff, the matter that's in each of them has an effect. And that's true. The matter of object 1 has an effect. The matter of object 2 has an effect also. More mass, more gravitational attraction. More mass, more gravitational attraction. They both increase in mass. They both would cause an increase in gravitational attraction. What else? Well, you might think the density or the shape might have something to do with it, but it really doesn't. So if we can think of these as like free body diagrams, we might draw them as dots or spheres. And we would really think about the center of mass of those two objects. So let's say I have an object here, which is object A. Let's say I have an object here, which is object B. Okay, and it doesn't matter. This could be a mass of, say, 5 kilograms. This could be a mass of 10 kilograms. Yes, I made the smaller size a larger mass because these could have different densities. The center of mass might be at that dot. The center of mass might be at that dot, something like that. If I double this mass, as you might predict, the gravitational attraction between these two things would double. If I double this mass, it would double. If I double both masses, the gravitational attraction would quadruple. Okay? So when I think about gravitation, F sub g, mass of A, or mass of object 1, actually I should call this 1 and 2, times the mass of object 2, those are both directly related to the gravitational force. Well, what else might affect it? As you might expect, the distance between these two things affects the gravitational force as well. And as you might expect, as the distance increases, the gravitational force weakens. Interestingly enough, it's not quite simple like that. It's not just an inverse relationship. It, in fact, is something called an inverse squared relationship. So if I think about this as a distance, oftentimes physics textbooks will call this distance r as a radius, and I'm a little perturbed why they do that, because it's the whole distance between here and here, not just half the distance, which you might think of as a radius. I'll call that a distance d. So we'll say this is over d squared. And in fact, inverse square relationships are very common in nature when you think about things that are three-dimensional. So if each of these was a sphere, and the dot in the center is the center of mass, we could think of them as a point source. Okay? And then you could think about that as being, this is a point in space, but the gravitational field created by that mass spreads out from that one single point into not one dimension or two dimensions, but three dimensions. So you're going from a single point to three-dimensional space, so things weaken very, very quickly. In fact, they weaken by a square factor. That's true of a lot of things, like light intensity, magnetic forces or electrostatic forces. Sound also decreases by an inverse square. So if you yell, the sound decreases. As you get twice as far away, it's a quarter the intensity it would be otherwise. So that's actually pretty interesting. Is that it? Well, it's not quite it. One of the things here, if we're looking for forces, and this would be in newtons, because all forces that we're measuring in science class and physics class are newtons, mass in kilograms, distance in meters, those units then, to go along with how our universe actually acts, we need a constant. And it is a fundamental gravitational constant. When we multiply it by all these things, would give us an answer in newtons. If we didn't have that constant, we get numbers which are proportionally correct, but they wouldn't make sense in terms of units that we use. So that universal gravitational constant is big G. Okay. So what is big G? Well, big G is 6.67 times 10 to the negative 11th. What are the units? Well, here I've got kilograms on top times 2 kilograms on top over meters squared on the bottom. I need to end up with newtons. So the units are newtons, meters squared, per kilogram squared. I'm not really concerned about the units, though. Just know that that is the number you would use. You should write this formula down on your formula sheet. You should write that constant down on your formula sheet. Those are things which are going to be pretty important. The other thing is that I want you to think about is that overall, when we're calculating things with this formula, oftentimes we're calculating things that would be very, very large. And in fact, things like the mass of the sun, the mass of the earth, other objects would be kind of important. We're calculating this. If this is really a small distance, and that's our constant, then a lot of times we would get very small numbers. And that's why we don't notice gravitational forces caused by things like the sink or this bottle of disinfectant or anything like that. They're tiny in comparison to other everyday forces we use. So to think about that, I'm actually going to calculate the gravitational force between these two objects. This looks to me to be about a half meter apart. So we're going to say that is 0.5 meters. So if I want to calculate the gravitational force between these two, I'm going to say F of G is equal to big G, which is this, 6.67 times 10 to the negative 11th, mass 1, 5 kilograms, mass 2, 10 kilograms, all that over 0.5 meters squared. So I'm going to ask you to go ahead and plug that into your calculator and see what you get. So there's going to be a question after this, because it's really important to know how to use order of operations correctly. And I'm going to go ahead and do that now. 6.67 e to the negative 11th times 5 times 10, and then I push the equal sign to get everything in my numerator, divided by 0.5 squared. So parentheses are probably my friend with that. And I get a number that's really small, and I don't want to use decimals, so I'm going to put it in scientific notation. And that ends up being 1.3 34 times 10 to the negative 8th newtons. So that's 0.000000001 334 newtons. That's ridiculously small amount of force, right? And those would be two pretty massive objects. That's about 11 pounds, that's about 22 pounds. At any rate, that's a tiny number, something you'd never be able to particularly feel compared to all the other forces around. So what would happen if we change some of these things? I'm going to go get into that next, because we want to think about things proportionally. So although that's the actual number of force, sometimes I don't particularly care about that. So for example, let's say I give this a fake number, a dummy number. Instead of 1.334 times 10 to the negative 8th newtons of force, let's say I call that, I don't know, 20 units of force. Now the question might be, what happens if I change some of these parameters? Okay, I'm going to get rid of these things now, except for that equation. My board has not been erasing very nicely today either. I apologize about that. So this condition I said happened to give us 20 units of force. What would happen if I say how many units of force we have if mass 1 doubled and the distance doubled? Well, let's try that. I could go through and put all the real numbers in for this equation again, and that would give me like those tiny little, those numbers with the negative exponents. But I've said that this equals 20 units of force. So what I want to do is I want to think about my initial condition and then a final condition when we've changed things. So initially, if I look at this equation, let's pick a dummy number for big G. Doesn't matter what it is. Simple number, 1. What about mass 1? Pick a simple number, simplest number, 1. Mass 2, simplest number, not 10, but 1. Distance between them, simplest number, not 0.5, but 1. 1 times 1 times 1 in the numerator is 1, over 1 squared in the denominator is 1. So essentially I get 1 overall quantity here. Now what I'm saying is that's equivalent to 20 units of force. So now what happens in this new condition? How have things changed? All right, well, the universal gravitation constant is always the same. That's why it's universal. As far as we know, again, never say never in terms of disproving things in science. So I'm going to always have that as still 1. What about mass of object 1? Well, mass of object 1 was doubled, so I'm going to put a 2 there. Mass of object 2 didn't mention anything about that, so we're going to assume that that stays the same. That's still 1. And the distance between them also doubled. That's over 2 squared. So 1 times 2 times 1 is 2 in the numerator. 2 squared is 4 in the denominator. That becomes 1/2. So 1 versus 1/2. That means if I went back to my units of force, if 1 was the condition where I had 20 units of force, now I would obviously have half of that, and that would be 10 units of force. We could do something similar with that. Do this again. Let's say mass 2 is halved, and the distance is 1/3 as much. So we're going to go through the same sort of thing right now. All right? Initial condition, still all 1s proportionally. New condition, big G, still 1. Mass of object 1 did not change, that's 1. Mass of object 2 was 1/2. In the denominator, the distance is 1/3 as much, so that's 1/3 squared. So what do I have? My numerator, I've got 1/2. Here I've got 1/9. 3 squared is 9, 1/3 is 1/9. Well, that's a little bit annoying. So essentially what we could say is this is 1/2 times 9. So this really is equal to 9/2, which is 4.5. So whatever force I had initially, I'd have 4.5 times as much. If I had 20 units initially, 4.5 times as much would be 90 units of force. So that's kind of how we go about that. One other thing here I want to go back to is some things with free body diagrams. So it's important to understand that a gravitational force is an interactive force between 2 objects. We aren't going to get into looking at 3 or more objects at the same time, although people can do that. It really is an interactive force between 2 objects. So let's say I've got my initial condition here. I'm going to draw a free body diagram. My free body diagram, if this is object 1 and this is object 2, well, gravity is an attractive force. So I would label this F of 2 on 1. What is that? The gravitational force of object 2 acting on 1. How about the gravitational force on object 2? Well, that's going to be caused by object 1, and it's going to be the same amount of force. Why? Well, Newton's third law of motion says forces exist in pairs, they point in opposite directions, and they act on 2 different objects. So that's something we learned early in the year. So this is F1 on 2. Those are equal in size, pointing in opposite directions. Okay. Well, what happens now if we've halved this mass, but then the distance gets much closer? Well, if that's true, I can't really draw these dots that much closer, but I can draw, I really should have done this with a different, very different color, so I'll make it red here. In this particular case, the force has increased a lot. So F of 1 or 2 on 1 is much bigger, and F of 1 on 2 is much bigger also. They're still equal to each other because of Newton's third law. One thing you might ask is, well, if the forces are always equal on each other, how come everything isn't always the same? Well, the forces are acting on different objects. So in this particular case, if we have an equal force on both these objects, this object has less mass, it's going to have a greater acceleration. This object has more mass, it's going to have a less acceleration. So the forces are equal, but the effects of those forces may not be equal. So in this particular case, there's one last thing I want to talk about, and that is big G versus little g. Big G is the constant for universal gravitation. And it's 6.67 times 10 to the negative 11th. Okay. Little g, which we can think of as acceleration in meters per second squared or newtons per kilogram, is a gravitational acceleration. How do we get little g? Well, let's think about this. Let's say we have an object on the surface of the Earth. The mass of the Earth is equal to 5.98 times 10 to the 24th kilograms, I think. I'm going to have to check that out. The radius of the Earth is also pretty big. So give me a second. I'm going to actually make sure I get my data correct. We'll go from there. All right, I did look up my data. That is the correct mass of the Earth. The radius of the Earth is 6.37 million meters. That's 6,370 kilometers and about 3,500 miles, but 6.37 times 10 to the 6 meters. So I want to think about a person standing on the surface of the Earth at that distance away. And I'd like to figure out what the gravitational force is between the Earth and that person. So to do that, I'd use this formula. Well, I'll go ahead and do that. That's going to equal big G, which is 6.67 times 10 to the negative 11th. Mass of person 1, we're saying is 100 kilograms. It's a pretty massive person, about 220 pounds. Mass of the Earth, 5.98 times 10 to the 24th kilograms. Radius of the Earth is 6.37 times 10 to the 6th meters. We've got to square that. It's very easy to forget to square that bottom term, by the way. And when I plug that in my calculator, if I do it correctly, I should get around 980 newtons. I do, I get around 983 newtons. So that is the force of the Earth acting on you, and that is the force of you acting on the Earth. So the question is how do we come up with this little g, this gravitational acceleration, and why is it the same for all objects? Well, if we have this and we think about it as an acceleration, the acceleration of objects due to gravity on Earth is A is equal to G. Well, an acceleration is just net force over mass. Okay. Well, what's the net force? It's the gravitational force, which is big G. In this case, it's M person, M Earth, over R squared. Divided by, now that's on the numerator, divided by the mass. Well, what mass? It's the mass of the person, because we're trying to find the acceleration of the person. So I'll circle that. That goes down here in the bottom. So essentially the mass of the person doesn't really matter, because it's both in the force equation and then the mass part of the equation. So little g, the acceleration on the surface of a planet, is related to big G times the mass of that planet, in this case it's the Earth, over the distance squared, or in this case the radius squared. So if we had the exact same mass of Earth, but it was twice the radius, we wouldn't have gravitational acceleration of around 10 meters per second squared. We'd have a quarter as much, of about 2.5 meters per second squared. So that's an example about how to think proportionally. Thanks for putting up with the long video. Oh, the magic word. Magic word. Electromagnetism. That's a good magic word.